Okay, so this is the advanced analysis portion. So I'm going to go a little bit faster with explanations, but I'm going to zip a little quicker for those who have a little bit more knowledge in Grasshopper. Or even if you don't, you can still follow along later, but you can kind of get the general gist of what I'm trying to do. There's also kind of data analysis that originates from formal analysis, not just using calculations, but creating new forms. So for example, let's say I actually want to create a little Grasshopper script or component that every time I subdivide a space like this, it gives me the square footage of a room. And it's some sort of plan maker, so that using this I can generate plans or kind of do subdivisions. And this would, you could imagine that this is incredibly helpful perhaps in a housing studio when you have a given housing unit and you want to divide it into areas of different ratios, or for a master plan where you want to kind of create different zones, maybe by creating circles, and trying to figure out how they intersect, what their volumes are. So let's tackle this at the line level. So I'm going to go and disable a lot of what we've done, just because we don't really need to look at it right now. Or actually, what I'm going to do, I won't disable it. I'll just grab this geometry and I'll move far out here, down here, and so we don't have to think about what we did earlier. So what I want to do is I want to use these lines to kind of create these different voids. How do I do that? Now, in Grasshopper, especially when you're doing this kind of analysis or anything, the specific tool you're using is actually really helpful. The same way in Rhino that you can, once you find an interesting tool like Wirecut or Cage Edit, that becomes a way or an amplifier of what you can do. In this case, I'm going to use a component called Surface Split. You can also find it by going to Intersection, to Physical, going into Surface Split, which says split a surface with a bunch of curves. So this takes as input a surface and a bunch of curves. And you can imagine that you could create a plane, use that as a geometry, and then plug that into the surface, plug the curves into curves, and then that way you get as an output 4 different types of surfaces. 3 are trimmed and 1 is an invalid surface, which is great. The question is, how do you know how big the surface is going to be? Well, we could have an infinitely large surface, an infinitely small, or something like that. We could just have a preset surface, but that seems kind of messy. And what happens, especially if we draw a few lines out here, and we'd have to move the surface over to compensate. So instead, let's create a component that, given the geometry, create bounding surface. And again, I'm using this as pseudocode because what we want to do is we want to get the curve geometry, plug it into create bounding surface, plug it into surface split. So let's actually make a cluster, and then let's go in to kind of figure this out. So these are the lines, wall lines, say. And I'm going to use the wall lines, and I'm going to, first of all, we want to create a surface around them. So one very convenient thing is called bounding box. There are a few ways to do this. I could use bounding box. I can use the bounding box, and it'll create a bounding box per object, but I can also right-click on it, click on union box, and it will try to get the bounding box of everything. There's also, and the thing about this is it's actually a 3-dimensional box that just happens to have height of 0 because all of our objects are on the XY plane. Actually, this is perhaps one of the best ways to do it. Another way to do it is to get the control points of the geometry, and then to use bounds 2D to get a domain. Actually, I'm going to flatten all the points because I want bounds to consider all the points together. Again, if I don't flatten it, then you can see that all the points are in different branches, and each branch representing each curve or polyline. So if I flatten it, it considers all the branches, and it gives me a bounds, a u value u and v values that I can then use to define a plane. The problem with control points is that you can imagine that I have a curve, and let's see, oh, this is interesting. Oh, I'm going to go out of the cluster, go back in. Actually, I'm going to go out of the cluster, make sure that it registers, go back in. And the thing about the cluster is that the curve is that in this case it worked because the control point was out here, or this is a union box actually, but the bounds actually may not encompass the curve because the control points and the curve are separate. So the union box is actually the best way to do this kind of a bounding box situation, but in this case we just have a flat box. So one way in which we can find the bounds of the box is, there are a few different ways. One is we can take the box, go to deconstruct box. When we plug it in, we'll get the x dimension, the y dimension of the box, and then we can make a plane using the dimensions in the x direction, dimensions in the x direction, dimensions in the y direction, plane. Another way that we could do is we could project the object onto the xy plane. If I use this button to only draw the preview geometry, you can see that I get all the same things. And it looks like they operate pretty quickly. Just because project seems unnecessary, I'll just go with this one. And so I'll take this out. So now, as a result, I have the geometry as an input, I have unioned the box, I've gotten the dimensions of it, I've created a new surface, and lo and behold, I've projected it out. So this is done what I wanted to do, create bounding surface, and outputs the bounding surface, and inputs the wires. So then, that's great. So if I plug this into a surface split, then I'm going to turn the preview on. I get all these different trim surfaces. So just to keep it simple, let's see what's going on here. Interesting. Let's try it again. Okay, so this is all great. The problem with this is that it's actually grabbing this surface and this surface also. So part of the reason is that when I'm splitting the surface with these curves, because the bounds of the surface is so tight, it's grabbing this area and this area also. And you'll see what I mean by if I grab the area of each of these surfaces, the area also gives us a centroid, right? So it's giving us this point, this point, this point, this point, because it's considering these lines as dividing lines. Which is all good, but that's not really what I want, because according to the lines I drew, these are the only internal points I have. So one thing I can do is I can expand the bounding surface a little bit. So okay, so what do I need to do? I have this plane and I want to expand it, or kind of increase the boundaries. One quick and dirty way is I could just scale the plane. So I can use the scale component, scale on object uniformly in all directions. Now it wants the base geometry, that's the plane, and it wants the center of scaling. So how do I determine that? So I could try to examine the plane, but I could get the centroid, that's done by the area. So if I plug the plane in, I also get the area, which is the center of the plane, or I also get the centroid, so I can plug the centroid into the center. And scaling, now it doesn't really matter because we just want it to be bigger. So let's just say like 1.2 is a good number. So then it's going to scale it larger than the outer bounds. And I'm just going to then plug this into our output. So that means that when we return, this is our bounding surface. So when we do the surface split, great, we only get these 2 points, or these 2 areas, which then we get these 2 centroids. Now, looks like we also get this point. That's okay, because as we go on further, you can look, there's an invalid surface and 2 trim surfaces, and it's clear that these are 2 trim surfaces, so we want to try to get those out as possible. So the question is, okay, how do we know what's an invalid surface and a trimmed surface? Now, a few ways to do this, and one way is actually we can just find a way to distinguish between these internal ones and then the outer surface. So let's try doing deconstruct BRAM. So if I plug this in, it's going to give me faces, edges, and vertices. So this just gives us the same thing. But this is interesting. So we have the first branch that has around like 16 curves, second branch has 4, second branch has 4. So actually, let's see what happens if we join the curves. Now this is even better. We have the first branch has 5 curves, the second branch has 1, the second branch has 1. And so it's pretty clear that this is one of them, and this is another one. How do we debug this? We can use the tree branch component. So we can plug this in and then say use the slider 1 to 2 or something like that. Oh yeah, of course the path does not exist. I'm going to simplify, so that's 0, 1, 2. So if I hold this, the 0th one are those 5 curves. The first one is that area, the second one is that area. So I'm right. This curve and this curve are the internal areas, and these 5 curves are the external ones. So then what I can do is I can say, okay, give me the areas that only have one parallel line curve, or in which the curves are closed or something like that. I've joined them together, so we want closed curves. Closed is a pretty good test. It'll tell us true or false. But the problem is, it looks like we get some false positives because it tells us this one is true. Really what we only want to know is, okay, do we have one polyline curve per branch? So what we need to do is we just need to scan each branch and see if the resulting curves is just of number 1 or multiple. So just to double check, let's try another curve. Okay, so we get a lot of different area points, and we still have this initial one that has like a bunch of different curves, but all the other ones have 1 curve each per branch, so that looks pretty right. So one way of finding those is to do a length, but not on the length of the curve, but on the length of the list. That way, we know the length of each branch. Another way to do that actually is to do tree statistics, and if you plug that in, it'll give you the length of each branch of the tree. Same thing, actually. But because we'll just stick with this, so then we'll say, okay, we want to find all the instances in which the length of the tree, or length of the branch rather, equals 1. It gives us true or false, and then we're going to use the dispatch command to grab these lines, use this true or false value, and then use this geometry. And so then all of a sudden now we have only these curves with the branch structure maintained that have internal volume or internal area. So then here we can use the area function. Actually, we didn't need this. So then this is going to grab us the area. And what we can also do is we can, use create maybe a planar surface. And then we can do the stuff we did earlier. So for example, we could do the bounds and remap. So I'm going to remap the numbers of the area, and then I'm going to get the bounds based on the area. So I'm going to remap all the numbers from 0 to 1, and I'm going to use the RGB color to recolor these surfaces. And so I'm going to use the preview component, plug the geometry to the preview component, plug the shader in here, and if I turn this preview off, and I hide everything but the preview, again, as is good practice if I'm using preview objects. Okay, everything is pink. Why is that? Again, we might have to debug. Let's plug this into here. We get 0, 1, 2, 3, 4, and 5. Those are branches. The boundary curves, on the other hand, they have also a similar branch structure. So then the question is, what's going on here? These values are all the same. Why is that? These areas are all different, however. The remapped numbers are all the same. So you can find it here by, the reason is the bounds it's using is always unique to each value. So, notice that this is not really a domain, it's 3079 to 3079. Instead, I want the bounds of all of the numbers, so I'm going to flatten the list. So it's giving us the right range, it's giving us the right numbers, and as you can tell, you can already see the kind of color distribution of light to dark. So you can imagine that as you start to subdivide, the larger ones are brightly colored. You could also imagine doing something like, say, going up and grabbing the standard deviation component, because we already made that in the standard deviation cluster, and then plugging the area values into here. And let's see what we get. We get 0.0 for each value, which makes sense because we don't want each value standard deviated. If we flatten, so then we get the standard deviation of everything, and then we can do a similar kind of remap thing as we did above. But in this case, we'll create our own domain, we'll construct it, we'll set it, say, force 0 to, and this is a pretty high number. I don't know where we're getting that from, so why don't we just say 50,000. And once we remap that, we're getting the standard deviation from 0 to 5. I'm going to use, again, the RGB component. And let's see, maybe I will color the walls with this. So I think the walls are being colored with this preview component, but I will drag this down here and I'll color these walls. So and I'll use all the colors. Okay, so what this is the larger the standard deviation, the higher the number, so the brighter it is. So the walls are colored by standard deviation, and so this is the more even the rooms get. You can see the walls are dark, and the air spaces are colored by the proportional size. So if we had, for example, within a bounding box, like a very big room and a very small room, the walls would be pretty bright. Let's see. But that's interesting. The standard deviation is very high. Oh, of course, the standard deviation goes up the more the variance exists. So thus, the standard deviation goes. The walls are darker, the more different the two spaces are. But if we took and just divided down to half, I suppose the walls should be relatively bright. That could also be that the standard deviation we're using is not quite adequately calibrated to work with the values we're throwing around. Right, 227691. That's pretty incredibly large. Yeah. So why don't we actually up the stakes a little bit. Okay, pretty interesting. And the standard deviation. It's also possible that I'm working with geometry that's way too big. Okay, so this is a little manageable. These are the areas, and the standard deviation that I'm getting is this much. In fact, I'm going to try to see if I can use the bounds of the numbers for the standard deviation. It looks like the standard deviation is sort of working. So, in any case, this is one tool that, would be very helpful, again, in either a site plan or some sort of housing studio in which you're trying to divvy up different spaces and do a very quick and dirty analysis of, okay, how are the spaces divided up. You could use different circles, have them intersect. Okay, and the reason why this volume isn't being colored is because of this line. This line. It doesn't like lines that just kind of stop. So in this case, you have these different colorations where you can quickly tell that these are the biggest, these are the smallest. So this is a pretty helpful and interesting way to do a kind of space influencing exercise. Remember that we started out with a Wallmaker. And I'm actually going to shrink this a little bit. We started out with this, and you could imagine that this would be a great way to or an interesting way to create some walls. And do some analysis on what kind of spaces you can get if you do some divvying up. And so the Wallmaker now, now there's this temptation to kind of, maybe divide up the large chunks or vice versa. And so the coloration that is created by doing this geometrical analysis, and that is then done by obtaining this calculation, is then driving the kind of output we desire, because it's modifying the feedback loop between what you're making and what you're analyzing.